Pulley, Part 2, with resistance. Let's say we have now a table, a book, and the table and the book are still pulled by the same box on the pulley. But between the book and the table now we introduce a board. The board has friction. So let's do the force diagram for the book. BK for the book. There's the weight of the book again. It's still 40 newtons down. The normal force is still 40 newtons up. It balances out. But the tension and the friction now, there's friction. The tension and the friction must balance. My net force is still 0. My acceleration is still 0. Right? So if I have friction, it must be balanced out my tension to give me a balanced force diagram. A first low example, acceleration is 0. Again, my box is still 10 newtons. So the box is also balanced with no acceleration. The whole system has no acceleration. The whole system is balanced out. So the weight of the box is 10 newtons, the tension is 10 newtons, and therefore the friction is 10 newtons. So the force of friction is 10 newtons. We solve what the force of friction is, what the friction is of book on board, by knowing the weight of the box. Now, the friction force is less than or equal to mu, coefficient times n. It's only equal to the max. The only equal one is the maximum. So we can figure out what this maximum is by putting some rocks in the box. I just put some rocks in that box there. I put the rocks in the box, and now the box is weighing 20 newtons. So if my box weighs 2 newtons, the tension is now up to 20 newtons, which means the tension is 20 newtons, and my friction is up to 20 newtons. Is this the maximum? No. I haven't gotten the maximum yet, because I still have enough friction. If I put more rocks in the box, and I put 30 newtons of rocks in the box, so now my tension is 30 newtons. And I got this balanced out. So what happens is, I've got more rocks in the box now, weight is 30 newtons of the box, the tension is 30 newtons, the force of friction of board on book is now 30 newtons. And I notice when I do this, just adding one more rock, the acceleration is no longer 0. The book starts to slide. When I now go one more rock, I'm at 31 newtons. So I've exceeded the maximum friction. Acceleration is not 0, therefore the net force is not 0. The box is falling, the box with the extra rock in it is now falling or accelerating down, falling from rest. So the box is accelerating, it pulls on the string of the rope that connects the two objects. So therefore there's a net force on the book also. As the book starts to accelerate, it goes from rest to start sliding to the right. So that means the tension at 30 newtons must be greater than the friction. But as soon as the thing starts moving, this friction is no longer static. You know kinetic friction is less than static. Usually it's about half. So let's pretend the kinetic friction is now 15 newtons. So my tension is greater than 15 newtons, so the book slides with some acceleration. The same exact acceleration that the box has. The whole system has the same acceleration that the box has with the rocks in it. The box with the rocks is accelerating down, the book is accelerating down with the same acceleration. That's because the weight has exceeded the maximum static friction. And now the book slides, or has kinetic friction because it's sliding. So I have an imbalanced force diagram on both objects. What is that tension though? If I share the same acceleration, if I exceeded the maximum, I can start using this equation. So I know that my equation for maximum static friction is equal to mu times n. That's when this friction is maximum. I found the maximum friction to be 30 newtons, because as soon as I exceeded 30 newtons, the book started sliding. So 30 newtons is my maximum static friction. So that's mu times the normal, which is 40 newtons. And so I can solve now for what my mu static is. Mu static is simply friction over normal when it's equal to the max, which is 30 over 40, which is 3/4, 0.75. This solves for mu of book on board. I simply increase the weight through the system to pull that book across the rough board to solve for the coefficient of friction between the two materials of book on board. This is the coefficient for static friction. If I increase the weight, I can increase the normal of the book, and I'm not going to change anything. So for instance, if I double up, if I have 2 books, so instead of 40 newtons of a book, I have 2 books, 80 newtons. That means my friction is going to increase to 60 newtons, because mu does not depend on anything but the book and board's material. I have 2 books side by side, 2 books on top of each other to increase the weight, increase the surface area. All it does is increase the friction, not the coefficient of friction. The coefficient of friction is set to be 0.75. It is independent of the surface area and the weight, independent of size and weight. It's simply a relationship between two materials. And it's unitless because those newtons cancel out. Now if I get this book to start sliding, because I now added more rocks, say 35 newtons of rocks are in this box, and the box pulls on the pulley to pull the book, the whole thing starts accelerating, it shares a common acceleration. Well, now I got a Newton's second law problem. The tension is greater than the kinetic friction to accelerate the book. Tension minus kinetic, tension to the right, kinetic to the left, so tension minus kinetic friction is the net force not equal to 0. It's equal to mass of the book times acceleration. My kinetic friction is mu k times the normal, let's say, which is 0.4 times 40, just making up these numbers. This gives me a 16 Newton kinetic friction. I just made up mu k to be 0.4. The normal is 40 newtons for this book still. My force diagram for my box is the weight of the box, which is now 35 newtons to make the whole system accelerate. And the weight has to be greater than the tension to make this thing accelerate down, which is tension minus weight. And that's minus tension minus the weight. The weight is down, so the weight's value is negative. It's a negative force downwards. So tension minus weight. But my acceleration and my net force are therefore downwards. So if weight is negative, then my net force for the box is also downwards or negative. So I have to have that negative ma. So I don't know my two tensions, I don't know my accelerations, but from what I gave you, you can figure out you know the mass, and so you have now weights and masses, you have knowns, and in your two equations here you have two unknowns, the tension and the acceleration. They have the same acceleration, they have the same tension, so if these two unknowns in two equations, you can solve what the tension and the acceleration is in this system given these values. Do so.